Right, this string from bx to ex represents all of the stuff in x's subtree, in the rooted tree starting at x. How do I maintain that? Using a data structure. So we're going to use something, a data structure we haven't yet seen. It will be in lecture 8. This is a time travel data structure, so I'm allowed to do that. So order maintenance data structure. You can think of this as a magical linked list. Let me tell you what the magical linked list can do. You can insert, I'm going to call it an item because node would be kind of confusing given where we are right now. You can insert a new item in the list immediately before or after a given item. Okay, this is like a regular linked list. I can, here's a regular linked list, right? And if I'm given a particular item like this one, I can say, well, insert a new item right here. You say, okay, fine, I'll just make a new node and relink here, relink there. Constant time, right? So in an order maintenance data structure, you can do this in constant time. Wow, so amazing. Okay, catch is the second operation you can do. Maybe I'll number these. This is the update. Then there's the query. The query is, what is the relative order of two nodes, of two items, x and y. So now I give you this node, and I say, which is to the left? Which is earlier in the order? I want to know, is x basically less than y in terms of the order in the list, or is y less than x? And an order maintenance data structure can do this in constant time. Now it doesn't look like your mother's linked list, I guess. It's not the linked list you learned in school. It's a magical linked list that can somehow answer these queries. How? Go to lecture 7. Okay, forward reference. Lecture 8, sorry. For now, we're just going to assume that this magical data structure exists. So in constant time, we can, this is great, because if we're maintaining these B's and E's, we want to maintain the order that these things appear in. If we want to create a new version, like suppose we were just creating version Z, well, it used to be everything without this BZ, EZ, and we just insert two items in here, BZ and EZ. They're right next to each other, and if we were given version X, we could just say, oh, well, look at EX, and insert two items right before it. Or you could put them right after BX. I mean, there's no actual order here, so it could have been Y first and then Z, or Z first and then Y. So it's really easy to add a new version. In constant time, you just do two of these insert operations. And now you have this magical order operation, which if I'm given two versions, I don't know, V and W, and I want to know, is V an ancestor of W? Now I can do it in constant time. So this lets me do a third operation, which is version V an ancestor of version W? Because that's going to be true if and only if BV is an EV nest around BW and EW. Okay, so that's just 3 tests. They're probably not all even necessary. This one always holds. But if these guys fit in between these guys, then you know now what this tells us, right? What we care about here is reading fields. When we read a field, we said, oh, we'll apply all the modifications that apply to version V. Before, that was a linear order, so it's just all versions less than or equal to V. Now, it's all versions that are ancestors of V. Given a mod, we need to know, does this mod apply to my version? And now I tell you I can do that in constant time through magic. I just test these order relations. If they hold, then that mod applies to my version. So W is the version we're testing, V is some version in the mod. I want to know, am I a descendant of that version? If so, the mod applies, and I update what the field is. I can do all pairwise ancestor checks and figure out what is the most recent version in my ancestor history that modified a given field. That lets me read a field in constant time. Constants are getting kind of big at this point, but can be done. Clear? A little bit of a black box here, but now we've gotten as far as reading, and we don't need to change much else. So this is good news. Maybe I'll give you a bit of a diff. So full persistence, fully persistent, theorem, done. Okay, same theorem, just with full persistence. How do we do it? We store back pointers, now for all versions. It's a little bit annoying, but how many mods do we use? There's lots of ways to get this to work, but I'm going to change this number to 2 times d plus p plus 1. Wait, what's d? D is the number of fields here. Okay, we said it was constant number of fields. I never said what that constant is. D for out degree, I guess. So p is in degree, max in degree. D is max out degree. So just slightly more. The main reason for this is because back pointers now are treated like everyone else. We have to treat both the out pointers and the in pointers as basically the same. So instead of p, we have d plus p, and there's a plus 1 just for safety. It gets my amortization to work, hopefully. Okay, not much else is. This page is all the same. Mods are still, you give versions, fields, values, reading. Okay, well, this is no longer less than or equal to v, but this is now with the version, sort of the nearest version that's an ancestor of v. That's what we were just talking about. So that can be done in constant time. Check it for all of them, constant work. Okay, that was the first part. Now we get to the hard part, which is modification. This is going to be different. Maybe I should just erase. Yeah, I think I'll erase everything. Except the first clause. Okay, if a node is not full, we'll just add a mod, just like before. What changes is when a node is full. Here we have to do something completely different. Why? Because if we just make a new version of this node that has empty mods, this one's still full. And I can keep modifying the same version. This new node that I just erased represents some new version. But if I keep modifying an old version, which I can do in full persistence, this node keeps being full, and I keep paying potentially huge cost. If all the nodes were full, and when I make this change, every node gets copied, and then I make a change to the same version, every node gets copied again. This is going to take linear time per operation. So I can't do the old strategy. I need to somehow make this node less full. This is where we're definitely not functional. None of this was functional, but now I'm going to change an old node, not just make a new one. In a more drastic way. Before I was adding a mod, that's not a functional operation. Now I'm actually going to remove mods from a node to rebalance. So what I'd like to do is split the node into 2 halves. Okay, so I had some big node that was completely full. Now I'm going to make 2 nodes. And this one's going to be half full. This one's going to be half full of mods. Okay, the only question left is what do I do with all these things? Basically, what I'd like to do is have on the one hand, I want to have the old node. It's just where it used to be. I've just removed half of the mods, the second half, the later half. What does that mean? I don't know. Figure it out. It's linearized. I haven't thought deeply about that. Now we're going to make a new node with the second half of the mods. This is more painful than I thought. In reality, these mods represent a tree of modifications, and what you need to do is find a partition of that tree into two roughly equal halves. You can actually do a 1/3, 2/3 splits. That's also in a future lecture, whose number I forget. So really you're splitting this tree into two roughly balanced halves. And so this 2 might actually need to change to a 3, but it's a constant. Okay, so there's what I want is for this to represent a subtree of versions. Let me draw the picture. So here's a tree of versions represented by the old mods. I'd like to cut out a subtree rooted at some node. So that this, let's just assume for now, this has exactly half the nodes, and this has half the nodes. In reality, I think it can be 1/3, 2/3. Okay, but let's keep it convenient. So I want the new node to represent this subtree, and this node to represent everything else. This node is as if this stuff hasn't happened yet. I mean, so it represents all these old versions that they're not in the subtree. This represents all the latest stuff. So what I'm going to do is, like before, I want to apply some mods to these fields. And I do whatever mods were relevant at this point, whatever had been applied, I apply those to the fields here. And so that means I can remove all of these mods. I only cared about these ones. Update these fields accordingly. I still have the other mods to represent all the other changes that could be in that subtree. Okay, so we actually split the tree, and we apply mods to the new node. Anything else I need to say? Oh, now we need to update pointers. That's always the fun part. So let's go over here. So old node hasn't moved, but this new node has moved. So for all of these versions, I want to change the pointer that used to point to old node should now point to new node. In these versions, it's fine. It should still point to old node because this represents all those old versions. But for the new version, for the versions in the subtree, got to point here instead. Okay, so how many versions, how many pointers could there be to this node that need to change? That's a tricky part in this analysis. Think about it for a while. If you think about this, I mean, it's really in this new node, whatever is pointed to by either here or here in the new node also has a return pointer. All pointers are bidirectional, so we don't really care about whether they're forward or backward. How many pointers are there here? Well, there's D here and there's P here, but then there's also some additional pointers represented over here. How many? Well, if we assume this magical 50-50 split, there's right now D plus P plus 1 mods over here, half of them. Each of them might be a pointer to some other place which has a return pointer in that version. So number of back pointers that we need to update is going to be this, 2 times D, 2 times P plus 1. So recursively update at most D 2 times D plus 2 times P plus 1 pointers to the node. The good news is this is really only half of them, or some fraction of them. It used to be, well, there were more pointers before. We don't have to deal with these ones. That's where we're saving, and that's why this amortization works. Let me give you a potential function that makes this work. Is minus C times sum of the number of empty mod slots. It's kind of the same potential, but before we had this notion of dead and alive nodes. Now everything's alive because everything could change at any moment. So instead, I'm going to measure essentially how much room I have in each node. Before I had no room in this node. Now I have half the space in both nodes. So that's good news. Whenever we have this recursion, we can charge it to a potential decrease. Phi goes down by, because I have a negative sign here, C times, 2 times D plus P plus 1, I think. Because there's D plus P plus 1 space here, D plus P plus 1 space here. I mean, we added one whole new node, and the total capacity of a node in mods is 2 times D plus P plus 1. So we get that times C. And this is basically just enough, because this is 2 times D plus 2 times P plus 2, and here we have a plus 1. And so the recursion gets annihilated by 2 times D plus 2 times P plus 1. And then there's 1 C left over to absorb whatever constant cost there was to do all this other work. So I got the constants just to work. Except that I cheated, and it's really a 1/3, 2/3 split, so probably all these constants have to change. Such is life. But I think you get the idea. Any questions about full persistence? This is fun stuff. Time travel. Yeah.
So in the first half of the thing where if there's room you can put it in,
Right.
I have a question about how we represent the version, because before when we said we store now, field, and value, it made more sense if now was like a timestamp or something.
Okay. Right. So how do we represent a version even here or anywhere when we do a modification, an update in the data structure, we want to return the new version? Basically that we're going to actually store the DAG of versions, and a version is going to be represented by a pointer into this DAG. One of the nodes in this DAG becomes a version. Every node in this DAG is going to store a pointer to the corresponding B character and the corresponding E character in this data structure, which then lets you do anything you want. Then you can query against that version whether it's an ancestor of another version. So yeah, I didn't mention that. Versions are nodes in here. Nodes in here have pointers to the B's and E's, and vice versa. The B's and E's have pointers back to the corresponding version node, and then you can keep track of everything. Good question. Yeah.
Remind me what D is again?
Oh, D was the maximum out degree. It's the number of fields in a node. Yeah, as defined right here. Other questions? Okay, a little breather. That was partial persistence, full persistence. This is unfortunately the end of the really good results. As long as we had constant degree nodes, in and out degree, we can do full persistence for free. Obviously, there are practical constants involved here, but in theory, you can do this perfectly. Before we go on to confluence, there's one positive result, which is, what if you don't like amortized bounds? There are various reasons amortized bounds might not be good. Maybe you really care about every operation being no slower than it was, except by a constant factor. We're amortizing here, so some operations get really slow, but the others are all fast to compensate. You can deamortize. It's called. You can get constant, worst case, slowdown for partial persistence. This is a result of Gerrit Brodel from the late 90s, 97. For full persistence, though, it's an open problem. I don't know if people have worked on that. All right, so some mostly good results. Let's move on to confluent persistence, where things get a lot more challenging. Lots of things go out the window with confluent persistence. In particular, your versions are now a DAG. In DAG, it's a lot harder to linearize a DAG. Trees are not that far from paths, but DAGs are quite far from paths, unfortunately. But that's not all that goes wrong. Let me first tell you the kind of end effect as a user. Imagine you have a data structure. It maintains, think of it as a list, I guess, which is a list of characters in your document. You're using VI or Word, your favorite, whatever. It's a text editor. You've got a string of words. And now you like to do things like copy and paste. It's a nice operation. So you select an interval of the string, and you copy it, and then you paste it somewhere else. So now you've got 2 copies of that string. This is, in some sense, what you might call a confluent operation, because, maybe a cleaner way to think of it is the following. You have your string. Now I have an operation which is split it. So now I have 2 strings. Okay, now I have an operation which is split it. Now I have 3 strings. Okay, now I have an operation which is concatenate. So I can, for example, reconstruct the original string. Well, actually, I have the original string. No biggie. Let's say, because I have all versions, I never lose them. So now, instead, I'm going to cut the string here, let's say. So now I have this and this. And now I can do things like concatenate from here to here to here. And I will get this plus this plus this. Okay, this guy moved here. So that's a copy-paste operation with a constant number of splits and concatenates. I could also do cut and paste. And with confluence, I can do crazy cuts and pastes in all sorts of ways. So what? Well, the so what is I can actually double the size of my data structure in a constant number of operations. I can take, for example, the entire string and concatenate it to itself. That will double the number of characters, number of elements in there. I can do that again and again and again. So in U updates, I can potentially get a data structure size 2 to the U. Kind of nifty. I think this is why confluence is cool. It's also why it's hard. So not a big surprise, but here we go. In that case, the version DAG, for reference, looks like this. You're taking the same version, combining it. So here I'm assuming I have a concatenate operation. And so the effect here, every time I do this, I double the size. All right, what do I want to say about confluent persistence? All right, let me start with the most general result, which is by Fiat and Kaplan, 2003. They define a notion called effective depth of a version. Let me just write it down. It's kind of like if you took this DAG and expanded it out to be a tree of all possible paths. Right? Instead of pointing to the same node, you could just duplicate that node and then have pointers left and right. Okay, so if I did that, of course, the size grows exponentially. It explicitly represents the size of my data structure. At the bottom, if I have U things, I'm going to have 2 to the U leaves at the bottom. So, but then I can easily measure the number of paths from the root to the same version. At the bottom, I still label it, oh, those are all V. They're all the same version down there. So exponential number of paths. If I take log, I get what I call effective depth. It's like if you somehow could rebalance that tree, this is the best you could hope to do. It's not really a lower bound, but it's a number. It's a thing. Okay. Then the result they achieve is that the overhead is log the number of updates plus, this is a multiplicative overhead. So you take your running time, you multiply it by this. And this is a time and a space overhead. So maximum effective depth of all versions, maybe even some of effective depths, but let's just say max to be safe. Sorry. So if you sum over all the operations, this is per operation. You pay basically the effective depth of that operation as a factor. Now, the annoying thing is if you have this kind of setup where the size grew exponentially, then the number of paths is exponential, log of the number of paths is linear in U, and so this factor could be as much as U, linear slowdown. Now, Fiat and Kaplan argue linear slowdown is not that bad, because if you weren't even persistent, if you did this in the naive way of just recopying the data, you are actually spending exponential time to build the final data structure. It has exponential size. Just to represent it explicitly requires exponential time. So losing a linear factor to do U operations is now U squared time instead of 2 to the U. So it's a big improvement to do this. The downside of this approach is that even if you have a version DAG that looks like this, even if the size of the data structure is staying normal, staying linear, so this potentially you could be doubling the size, but we don't know what this merge operation is. Maybe it just throws away one of the versions or does something, somehow takes half the nodes from one side, half the nodes from the other side. Maybe these operations do preserve size. Then there's no great reason why it should be a linear slowdown, but it is. Okay, so it's somewhere, it's all right, but not great. And it's the best general result we know. They also prove a lower bound. So lower bound is sum of effective depths, total bits of space. Okay, what does this mean? So even if this is not happening, the number of bits of space you need, in the worst case, this does not apply to every data structure. That's one catch. They give a specific data structure where you need this much space. So it's similar to this kind of picture. Won't go into the details. And you need this much space. Now this is kind of bad because if there's U operations and each of these is U, that's U squared space. So we actually need a factor U blow up in space, looks like. But to be more precise, what this means is that you need omega E of V space and therefore time overhead per update if, this is not written in the paper, queries are free. Implicit here, they just want to slow down and increase space for the updates you do, which is pretty natural. Normally you think of queries as not increasing space. But in order to construct this lower bound, they actually do this many queries. So they do E of V queries and then one update. And they say, oh, well, the space had to go up by an extra E of V. So if you only charge updates for the space, then yes, you have to lose potentially a linear factor, this effective depth, potentially U. But if you also charge the queries, it's still constant in their example. So open question, for confluent persistence, can you achieve constant everything? Constant time and space overheads, multiplicative factor, per operation, both updates and queries. So if you charge the queries, potentially you could get constant everything. This is a relatively new realization. And no one knows how to do this yet. Nice challenge. I think maybe we'll work on that in our first problem session. I would like to. Questions about that result? I'm not going to prove the result, but it is fancy rebalancing of those kinds of pictures to get this log. There are other results I'd like to tell you about. So brand new result. That was from 2003. This is from 2012. No, 11. 11, sorry. It's SOTA, which is in January, so a little confusing. Is it 11? Maybe 12. Actually, now I'm not sure. It's February already, right? A January, either this year or last year. It's not as general a transformation. It's only going to hold in what's called a disjoint case, but it gets a very good bound. Not quite constant, but logarithmic. Okay, logarithmic would also be nice. Or log n, whatever n is. So pick your favorite n. Number of operations, say. Okay. If you assume that confluent operations are performed only on two versions with no shared nodes. Okay, this would be a way to forbid this kind of behavior where I concatenate the data structure with itself. All the nodes are common. If I guarantee that maybe I slice this up, slice it, dice it, whatever, and then remerge them in some other order, but I never use two copies of the same piece, that would be a valid confluent operation over here. This is quite a strong restriction that you're not allowed. It won't even, if you try to, who knows what happens. Behavior is undefined, so it won't tell you, oh, those two versions have this node in common, you've got to make a second copy of it. So somehow you have to guarantee that confluent operations never overlap, but they can be reordered. Then you can get order log n overhead. N is the number of operations. I have a sketch of a proof of this, but not very much time to talk about it. All right, let me give you a quick picture. In general, the versions form a DAG. But if you make this assumption, and you look at a single node, and look at all the versions where that node appears, that is a tree, because you're not allowed to remerge versions that have the same node. So while the big picture is a DAG, the small picture of a single guy is some tree. Okay, I'm drawing all these wiggly lines because there are all these versions where the node isn't changing. This is the entire version DAG, and then some of these nodes, some of these versions, I should say, that node that we're thinking about changes. Okay, whenever it branches, that's probably because the actual node changed, maybe, I don't know. Anyway, there are some dots here where the version changed. Some of the leaves, maybe it changed, maybe some of them hasn't yet. In fact, let's see. Here, where it's changed, it could be that we destroyed the node. Maybe it's gone from the actual data structure. But there still may be versions down here. There could be, it's not really a tree, it's a whole DAG of stuff down there. So that's kind of ugly. Whenever the node still exists, I guess that is an actual leaf of the DAG, so those are okay. But as soon as I maybe delete that node, then there can be a whole subtree down there. Okay, so now if you look at an arbitrary version, so what we're thinking about is how to implement reading, let's say. Reading and writing are more or less the same. I give you a version, I give you a node, and I give you a field. I want to know what is the value of that field, that node, at that version. So now, where could a version fall? Well, it has to be in this subtree, because the node has to exist. And then it's maybe a pointer. The pointer could be to another node, which also has this kind of picture. They could be overlapping trees. In general, there are three cases. Either you're lucky, and the version you're talking about is a version where the node was changed. In that case, the data is just stored right there. That's easy. So you can just say, oh, how did the node change? Oh, that's what the field is. OK, follow the pointer. A slightly harder case is it's a version in between two such changes. And maybe these are not updates. So I need to know I sort of want to know what was the previous version where this node changed in constant time. It can be done, not constant time, actually, logarithmic time, using a data structure called link cut trees. Another fun black box for now, which we will cover in lecture 19, far in the future. Okay. Then, well, that's one case. There's also the version where maybe a version is down here in a subtree. I guess then the node didn't exist. But, well, all these things can happen, and that's even harder. It's messy. They use another trick, which is called fractional cascading, which I'm not even going to try to describe what it means, but it's got a very cool name, because we'll be covering it in lecture 3. So stay tuned for that. I'm not going to say how it applies to this setting, but it's a necessary step in here. In the remaining 0 minutes, let me tell you a little bit about functional data structures. So, beauty of time travel. Functional. I just want to give you some examples of things that can be done functionally. There's a whole book about functional data structures by Okazaki. That's pretty cool. A simple example is balanced BSTs. So if you just want to get log n time for everything, you can do that functionally. It's actually really easy. You pick your favorite balanced BST, like red black trees. You implement it top down, so you never follow parent pointers. So you don't need parent pointers. So then, as you make changes down the tree, you just copy. It's called path copying. Whenever you're about to make a change, make a copy of that node. So you end up changing you copy all the changed nodes and all their ancestors. There's only log n of them, so it takes log n time. Clear? Easy. It's a nice technique. Sometimes path copying is very useful, like link cut trees, for example, can be made functional. You don't know what they are, but they're basically a balanced BST, and you can make them functional. We use that in a paper. All right, DEX. These are doubly ended queues, so it's like a stack and a queue and everything. You can insert and delete from the beginning and the end. People start to know what these are now, because Python calls them that. But you can also do concatenation with DEX in constant time per operation. This is cool. DEX are not very hard to make functional, but you can do DEX, and you can concatenate them like we were doing in the figure that's right behind this board. Constant time. Split is a little harder. That's actually one of my open problems. Can you do lists with split and concatenate in constant time? Functionally or confluently, persistently, or whatever. Another example, you can do a mix of the two. You can get log n search and constant time DEC operations, is you can do tries. So a trie is a tree with a fixed topology. Think of it as a directory tree. So maybe you're using subversion. Subversion has time travel operations. You can copy an entire subtree from one version and stick it into a new version, another version. So you get a version DAG. It's a confluently persistent data structure. Not implemented optimally, because we don't necessarily know how. But there's one paper, this actually came from the open problem session of this class 4 years ago, I think. It's with Eric Price and Stefan Langerman. You can get very good results. I won't write them down because it takes a while. Basically log the degree of the node's factor and get functional, and you can be even fancier and get slightly better bounds like log the degree and get confluently persistent with various tricks, including using all of these data structures. So if you want to implement subversion optimally, that is known how to be done, but hasn't actually been done yet because there are those pesky constant factors. I think that's all. What is known about functional is there's a log n separation. You can be log n away from the best. That's the worst separation known between functional and just a regular old data structure. It'd be nice to improve that. Lots of open problems here. Maybe we'll work on them next time.